Now we'll turn our attention to finding arc length and polar coordinates. And I'm going to show you the formula, but I'm not going to go through a proof because we've already done arc length in 2 other instances in the class, and it's not much different from those. So here's the formula. Let f be a function whose derivative is continuous on an interval from an angle measure alpha up to an angle measure beta. The length of the graph of r equals f of theta from theta equals alpha to beta is L equals the integral from alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. Now you can certainly see remnants of the arc length formulas that we've seen in the past. So it's not much of a stretch as to exactly where this particular function comes from. So let's see an example how to use it. So let's find the arc length of the cardioid r equals 2 plus 2 cosine theta. And this should have an interval to work with, so let's just go from 0 to 2 pi. Oops, 2 pi I meant to write, obviously. Okay, so let's find this arc length. The first thing that we'll do is just set up based on the problem given. So according to the formula, the arc length here is the integral from 0 to 2 pi, and it's going to be the square root of the original function of theta squared, so 2 plus 2 cosine theta squared, plus the square of its derivative. So the derivative of 2 plus 2 cosine theta, derivative of a constant, of course, is 0. The derivative of 2 cosine theta would be negative 2 sine theta. Now, what we're hoping for in order to evaluate this integral exactly is some way that maybe the Pythagorean theorem can help us out in writing what we have underneath the square root as a perfect square so that we can get rid of the square root altogether. So often there's some trig substitutions that need done here, but most of the time it's really just basic ones like maybe a double angle, but very often it's usually just Pythagorean identities. So let's first expand 2 plus 2 cosine theta quantity squared and see what that does for us, see what we can get from there. So squaring that out, I would have 4 plus 2 times 2 times 2 cosine theta, so that would be 8 cosine theta. And the square of the second would be 4 cosine squared theta. And the last part here, I can square negative 2 sine theta and make it positive 4 sine squared theta. Okay, so the last 2 terms that come about here, I think we can see a little bit of some remnants of the Pythagorean identity occurring here. So for instance, if I just went off to the side, I could show 4 cosine squared theta plus 4 sine squared theta. There's a common factor of 4, which I can pull out. And the nice thing about that, it leaves me the Pythagorean identity. Cosine squared plus sine squared is 1. So this just results in 4. So I can take those last 2 terms, replace them with the constant 4. And in doing so, I can also take what would be the constant 4 added to the other constant 4, and that would make an 8. So 8 plus 8 cosine theta d theta. Okay, now let's see what we can do here. So 8 is a constant, and we can always pull constants out from underneath a radical. Whether or not it's a perfect square doesn't really matter. It's still a constant, and it can be pulled out of the integral. But that would leave me a 1 plus cosine theta underneath there. So what could we possibly do with that? Oh, and I must have been thinking 4 in my head when I wrote the upper value here, because clearly that's still 2 pi. Oh, I apologize for that. All right, so 0 to 2 pi, square root of 8 times 1 plus cosine theta d theta. All right, so what would be nice is if we could rewrite this so that there's a perfect square involved and we could take the square root and basically remove it from the question. So we can almost do that using some different identities. If you'll recall, there is an identity which is known as the power reducing identity. We've talked about that quite a bit in this class. So that's cosine squared theta 1 plus cosine 2 theta all over 2. Now these identities don't have to be used as is. We're free to manipulate these as we please here. So for instance, one thing I could do is I could multiply both sides of this by 2, and I could say 2 cosine squared theta is equal to 1 plus cosine of 2 theta. And another thing I could do is make a substitution. So I could say, like, I have 1 plus cosine theta and not 1 plus cosine 2 theta here. So I can make a substitution saying that this is like m equals 2 theta, so that theta is m over 2. And then what I could write this as would be 2 cosine squared of m over 2 is equal to 1 plus cosine of m. And of course, the m versus theta is irrelevant. It's just the name of a variable at this point. And so I really could rewrite 1 plus cosine theta as 2 cosine squared theta over 2. So let's do that. 0 to 2 pi. Still have this factor of 8. And then I'm rewriting 1 plus cosine theta as 2 cosine squared of theta divided by 2. Now, a couple of things are really nice that just happened here. First off, I have this factor of 8 and a factor of 2, which are going to multiply to 16. And those are perfect squares, which is great. It's not necessary, but it's really nice because that means I have an integer on the outside of this integral. On the outside of the square root. And then left over is cosine squared of theta over 2, which means that the square root of that would be cosine of theta over 2 d theta. And now I have no square roots left. And that enables me to finish out evaluating this arc length. So if I find the antiderivative of 4 cosine theta over 2, of course the 4 can come off to the side. When you integrate cosine, that results in sine. So I'm going to have sine of the theta over 2. But then you divide by, like if it was cosine 2 theta, you would divide by 2. So in this case, we're going to divide by 1/2, which is the same thing as multiplying by 2. Then that's going to get integrated from 0 to 2 pi. So effectively, I have 8 times the sine of 2 pi over 2, which is pi, minus the sine of 0 over 2, which is 0. All right, now the sine of 0 is 0, and in fact, the sine of pi is also 0. So what happens here is I end up with 8 times 0, which is 0. Okay, so that's a little strange because recall here this was an arc length. All right, so let's take a look here, because it looks like this graph doesn't exist if its arc length is 0. So I'm going to pull up the calculator and we will graph this thing. Okay, well, let's get in the right mode here. Let's be in radian mode and change the graph type to polar. Then under y equals, I have the graph here. The original function was 2 plus 2 cosine theta. And the window settings here, 0 to 2 pi, that's great. Theta steps, that's great too. And I think the -8 and +8 here, I think that was just set for the screen to have as many pixels, wide as it does tall. So if I hit graph, okay, here's my graph. Now, the thing is, what's happening is with arc length, we're basically getting some negative values that are canceling out. So we have to be maybe a little bit more careful and rely on symmetry sometimes with these arc lengths of polar coordinate graphs. So I can see, this cardioid graph is definitely symmetric about the upper portion of the graph and the lower portion of the graph. So perhaps if I only calculated from 0 to pi and then doubled that, then I would get a better response. So let's do that. Let's try this and see what happens. So we'll just go from, say, this step right here down to this step. And we'll say that this is equal to 2 times the integral from 0 to pi. And this is based on symmetry. And the integrand is still the same. So 4 cosine pi over 2 d theta. 2 times 4 gives me an 8. And then I would have, of course, sine of pi over 2 times 2 again, same integral function or antiderivative. And then I'm going from 0 to pi instead of 0 to 2 pi. So this results in a multiplier of 16 times the sine of pi over 2 minus the sine of 0 again. But I think that's okay, because even though this one results in 0, this one, pi over 2, results in 1. So my final answer is an arc length of 16. And I did that on purpose because I wanted you to see that you have to sometimes be careful when dealing with arc length of non-functions, so they don't pass a vertical line test, because you've got cancellation that might occur. And so you might have to rely on some sort of symmetry in order to come up with those values.